Okay, so far what we have done is we have talked about EM radiation behaving like particles called photons, right? Not? So that means what people thought about EM radiation, which were waves, now you realize that you could also describe EM radiation as particles called photons. Otherwise, you cannot explain the phenomena like, for example, photoelectric emission and line spectra. Okay, which includes emission and absorption spectra lah. So all these phenomena are based on the assumption that EM radiation are photons, that means particles, right? Not? But the problem is, are EM radiation only particles called photons? Because there are also other observations that show that EM radiation behave as waves. Can you remember which phenomena prove to you that EM radiation also behave as waves? For the example, diffraction. Yes. Diffraction, when a wave passes through a gap, it will spread. But when a particle passes through a gap, will it spread? When you walk through the door, do you become fatter? Terence? Right or not? No, right or not? Okay, not sure right now. Okay, anyway. So, the thing is, only waves will spread. Furthermore, let's talk about interference. When the two waves, for example, two light, if EM radiation, if they meet in phase, we know the constructive interference. They become brighter. Then they meet out of phase, anti-phase, 180 degrees out of phase, then they get destructive interference. Then you cancel each other. Do particles behave like that? If you lie down on how mean, do you become one bigger person?
Yes.
Or do you destroy each other? No, right or not? So only waves behave like that. Particles don't. So therefore, EM radiation, they do exhibit wave properties. So the conclusion is, are EM radiation waves or particles? So the answer is, since nobody knows, is they can behave like both, but depending on situation. Correct or not? Right? Certain situations they behave as waves, certain situations they behave as particles, so we call it wave-particle duality. Alright, so then this guy de Broglie, so de Broglie, he said, hey, if waves can behave as particles, that means EM radiation, which was originally thought as waves, can behave as particles, why don't particles behave as waves? For example, can you behave as a wave or not? Let's give it a try. Okay, let's take the Terence for example. So let's find his equivalent wavelength if let's say he was a wave. So the formula is actually given by this de Broglie's equation, which is lambda, the equivalent wavelength, they call it de Broglie wavelength, equals to Planck constant over the momentum of the particle, which is mass times velocity lah. So that's what we're going to do. So we're going to substitute the Planck's constant here. And Terence, your mass, I suppose, is about 60? Huh? About, I think, 60 kg lah. And let's say, how fast do you walk? How many meters per second? 5 Faster than Usain Bolt Okay, cannot be. You are maybe 1/5 1 meter per second. Okay. So what will happen is, you can calculate this out and you will get about 10 to the power of negative 35 meters, which is 0.00000 many zeros, right? Which is almost 0. So therefore, you will not exhibit wave properties. Okay, but you see, this equation would be valid then for very small particles, example, electron. So the mass of an electron is how much? 9.11 times 10 to the power negative 31. So can you see, when you have 10 to the power negative 34 divided by 10 to the power negative 31, you can get a bigger number. So therefore, the wavelength would be much bigger than 0. So it could possibly exhibit wave properties. So what they did was, they tested it out by comparing it with the X-rays. So what is a typical wavelength of X-rays? X-rays wavelength is smaller than 10 to the power negative 9 meters. So the biggest is about 10 to the power negative 9 meters. So let's use this value and substitute into the de Broglie's equation to find out the velocity that you must give the electron. So you substitute 6.63 times 10 to the power negative 34, and then you substitute is 9.11 times 10 to the power negative 31, and then times the V. So what is the speed you must give the electron? See whether it's achievable or not. Quickly calculate. Okay, so 7.28 times 10 to the power 5 meter per second. Is it achievable? Definitely, because the speed of electrons typically is between 10 to the power 5 to 10 to the power 7 meter per second. We can actually achieve all these speeds easily. So 10 to the power 5, piece of cake. Okay, so what experiment did they do to prove this? Okay, look at the next slide. So this guy, these two guys, Derrison and Germer, right? So what they did was they compared these electrons to X-rays. So how did they prove whether electrons can behave like waves? If electrons can be diffracted. If electrons can be diffracted, that means it can behave as waves. Because only waves can undergo diffraction, not particles, right? So how did he do the diffraction of electrons? So he based it on the diffraction of X-rays, because it's comparing X-ray, right? So normally, when you're using X-rays, that means if this was a graphite or a thin metal foil, and if you direct a beam of X-rays, so let's forget about this. This is the experiment he did with electrons. But if you were to direct X-rays onto a thin metal film or graphite, as long as crystalline solid, what will happen is, because crystalline solids have this regular spacing, regular pattern, so the spacings between the atoms or molecules are regular. So what happens is, when the X-ray passes through the gaps, right, the spacing there, it will start to diffract. So it acts like a three-dimensional diffraction grating. Because you have spaces between the atoms, okay, if I were to draw, you have spaces which are vertical. At the same time, you also have spaces between them which are horizontal, right? And then you also have depth, so it goes multiple diffraction. So what comes out, I mean, after the X-ray passes through the thin metal foil, you will definitely get concentric circles. I mean, circle over circle over circle. This is if you're using X-ray. So since I want the electrons to behave like X-ray, I didn't know what speed to give it right now. So if I gave it that speed, so it will have the same wavelength as X-rays. So when I direct this beam of electrons, so this is actually a beam of electrons, because the cathode, all right, here hits up the filament, then the electrons come out from the cathode, accelerates to the anode at very high speeds, at the speed that we want, then hits the thin graphite film or thin metal foil. So it should give you the same observation as X-ray, which are concentric circles showing diffraction, if they are waves. But if they cannot behave as waves, then what will you see? If they cannot behave as waves, that means that the electrons will just pass through this gap, right now. Agree? Agree? The electrons will just pass through these gaps. So what you will see on the film, actually not film, phosphor screen, it will be just dots, like this. If they behave as particles, that means they cannot spread. But if they can spread, they will form concentric circles like this as well. So what did they see? Obviously, concentric circles. So this proves that electrons actually spread when they pass through the thin metal foil or thin graphite film. So showing that electrons can be diffracted. So this shows that particles can also behave as waves. So you will need to memorize this setup they asked you to draw before. How to draw the experiment to prove that particles can behave as waves. So this is the one you have to show. Particles behave as waves, the diffraction of electrons. Okay? Right. So by the way, do you know why they use a phosphor screen or a fluorescent screen, sometimes they call it? It's because when the electrons strike the phosphor screen or fluorescent screen, it will actually glow. So the pattern that you see here is when the electrons strike it. So remember, the pattern which are concentric circles is because of three-dimensional diffraction. Because there's gaps horizontally, vertically, and also in the z direction. So the pattern you get are concentric circles.